Even though this video is about the quadratic formula, I'd like to begin it by doing a complete the square problem. And we're going to complete the square using this literal equation, ax squared plus bx plus c equals 0. We begin by subtracting the constant term to the other side of the equation, as we normally do when we complete the square. And since there's a leading coefficient of a, we're going to divide through by a at the very beginning. This is going to give us x squared plus b over ax blank is equal to negative c over a. At this point, we need to cut the coefficient in front of x in half. That means multiplying by 1/2, and we will have b over 2a. Squaring this, we would then have b squared over 4a squared to add into the blank on the line above. And I'm going to add b squared over 4a squared to the other side of the equation to keep the balance. Now we will insert the x on the left, the parentheses around it, the quantity squared. And on the right, we need to combine like terms. We need a common denominator of 4a squared. So the denominator is being multiplied by 4a, so the numerator will get multiplied by 4a, and we'll have negative 4ac. So on the right hand side, the denominator will be 4a squared, and the numerator will be b squared minus 4ac. Now what we want to do is square root each side of the equation. On the left, we will have x plus b over 2a, technically in absolute values, but when we take the absolute values off, we'll have a plus or minus sign on the right hand side. The numerator will be the square root of b squared minus 4ac, and the denominator is a perfect square and becomes 2a. Now all we need to do is subtract the b over 2a off of each side, and we will have negative b plus or minus the square root of b squared minus 4ac all over 2a. And that right there is the quadratic formula, which you'll want to memorize. So what we've just done is a derivation of where the quadratic formula comes from, and if you know the values of a, b, and c, you can just substitute them into this formula to be able to solve for the solutions of this equation. Now let's use the quadratic formula. Rather than substituting the values of a, b, and c directly into this, and by the way, a will be the 2, b will be the 3, c will be the negative 7, I'd like to split my quadratic formula problems into two different parts. The first thing I do is I evaluate b squared minus 4ac. That's the expression underneath the radical, and it's called the discriminant. When I do so, I'm going to have 3 squared minus 4 times 2 times negative 7. 3 squared is equal to 9, and when we multiply the 4ac together, we're going to have plus 56, and that gives us 65. Then I move on to the rest of my quadratic formula, and the reason I do this to start is if that had been a negative 65, I would have known I've got a square root of a negative and I'd have imaginary solutions. And we can tell things about our solution set just from looking at the value of this discriminant. Now on the right hand side, I'm going to write the quadratic formula. T equals negative b plus or minus, and instead of b squared minus 4ac, we know that value is 65 all over 2a. Substituting in b and a, we have negative b becomes negative 3 plus or minus the square root of 65 all over 2a. Well, that's going to be 2 times 2, which is 4, and there we have our solution set. And notice how little space this took up since we evaluated the expression under the radical first before we substituted it in. This next problem is in standard form, and we could use the values as fractions in the formula, but most of us would probably prefer to clear the fractions by multiplying through on each side by the least common denominator 6. This will end up giving us 4p squared minus p plus 3 is equal to 0, and then we can identify a, b, and c easily with integers, b being negative 1. Let's split this into two parts and first find b squared minus 4ac. That will become negative 1 squared. Notice how I use parentheses around the negative 1, minus 4 times a, which is 4, times c, which is 3. That becomes 1 minus 48, which is negative 47. Notice how we have the square root of negative 47, and we know we're going to have imaginary and complex solutions. So p is going to equal negative b plus or minus the square root of negative 47 all over 2a. And substituting in those values, p will be negative b, that's negative of a negative 1, which is 1, plus or minus I root 47 all over 2 times 4, which is 8. Now note that this solution is not in a plus or minus bi form. You may need to rewrite your answer as 1/8 plus or minus the square root of 47 over 8i to get it into this nice neat a plus or minus bi, depending upon your teacher and or your homework system that you're using.